just a quick background. I've provided a picture so you can kind of put a face to the name here. Excuse me, I'm a little bit hoarse today. I'm a professional engineer with a mechanical background working out of Fort Worth for Jacobs. And I've got connections with Tim and CIBSE ASHRAE from working over in Reading for 2 years. And I came back here about a year ago. And I get real into energy and sustainability work, and life cycle costing has naturally come out of that. I did a master's in business finance, and kind of been trying to marry some of that up with the engineering work. So I'll go ahead and dive in here. So why are we looking at life cycle costing? Sustainability is kind of a big reason this has been, things have been shifting towards this. And the main reason being that we're typically trying to reduce operating costs by some kind of capital cost investment or expenditure. And we've usually got to justify some kind of return on investment to do that. And part of what I'm going to say here today is that building services engineers are pretty well positioned to inform this kind of thing. Traditional cost consultants at times often concentrate mostly on capital costs, and it's a lot of times up to engineers to get into some of this nitty-gritty.
Scott, if you
just a quick.
Scott, if you just get closer to your phone and speak up a little, we're in a large room here and it's not terribly loud.
Okay, apologies. I'll speak up a bit. So on definitions here, there's these concepts of whole life costing and life cycle costing. And I'd say you're going to see whole life costing a bit more mentioned in the UK rather than in the US. But the ISO standard 15686 actually defines it here, where whole life costing gets a bit more into externalities, business income, and some other sources not just related to capital costs and energy. So for most building work, it does concentrate more on the LCC side of things. That's the term I use. And there is a bit of confusion on this issue as well. I just wanted to state that life cycle assessment is sometimes used interchangeably, but it's more focused on life cycle environmental performance, such as carbon emissions from production and transport and so on. So here's a quick overview of what the main components are for accounting for life cycle costs. There's a few different ways to approach capital costs, usually starting out with less detail, where you're saying, here's a rule of thumb. You know, I have the example of installed cost per kilowatt peak of PV, and I definitely recommend going with installed cost figures. That's, you know, just doing material costs usually doesn't cut it. And these are typically the most certain costs that we get to look at with life cycle, just because they're pretty much in the here and now or within a year or two. O&M costs. Energy is obviously a big one, but maintenance shouldn't be looked over either. There's definitely data out there for maintenance costs for predictive and so on. I usually say that maintenance costs tend to track inflation, whereas energy costs we consider a bit separately because they're more volatile. Residual costs is one that may or may not be included. A lot of the time, building services equipment, boilers and so on, it can actually cost more to have them decommissioned and haul away than the residual value is really worth in scrap. So a lot of times this gets left off entirely. And unless you're doing a pretty large infrastructure project, I probably wouldn't be too concerned with that line item. One big thing is getting the client bought in on the LCC methodology. We basically need to tailor this to what the client's capital budgeting requirements are. And when I get into discount rate and escalation rate on energy consumption, those things should be agreed with them whenever possible, or simply using their figures if they're willing to give those out. Service life for equipment is a pretty important figure. It's not usually something there's a consensus on, and I know, for instance, a number of product manufacturers, if they're hoping to have their equipment look more attractive, they'll give it maybe a bit longer service life than we might expect out of them. Or vice versa, if someone is wanting to make it look unattractive. So definitely be cautious of this one. And I just mentioned CIBSE Guide M because it does have an appendix on a number of agreed upon service life, so that's something you can cite. Time value of money. This is something that often gets left out of some of the higher level life cycle cost analyses, and I would argue for more than kind of high level energy conservation measure work. When you're trying to do it in more detail, we should include discounting for it. Just a little bit of background here and how these discount rates are determined. Most people are probably aware that Bank of England, Federal Reserve here in the U.S., they tend to encourage 2 to 3% inflation year over year, for better or worse, and that typically works its way into the prices we see. And it's fluctuated over time, but I kind of recommend about a 3% inflation rate. I've got a bibliography at the end of here showing sources for UK and the US on life cycle costing, but for the most part, HM Treasury Green Book is kind of the source for discount rate information used for government projects in the UK, and National Institute for Standards of Technology in the US, that's it as well. And both of them advocate using real discount rates. So they've already had inflation removed from the figure, or it's already accounted for. Into selecting the discount rate. Basically, discount rate selection is based on this concept of opportunity cost, and this is true for all sorts of investment types. And there's also the desire to determine a discount rate by looking at investments with a similar level of risk or uncertainty in return. A lot of capital budgeting decisions are made using the firm's hurdle rate, which is often their weighted average cost of capital, which I guess this definition's on the next page here. Often, if it's capital improvements for facilities, the opportunity cost is actually just an interest-bearing bank account or a sinking fund. Sometimes just looking at yield on government bonds, and even returns on some previous projects, which can be maybe even more informative for the level of risk that you're going to see. And this is just the quick breakdown of real versus nominal interest rates. So nominal has included the inflation figure there, and real has got it taken out. Opportunity cost is definitely ultimately down to the client in terms of what they like to see. It's a macroeconomic concept as well, because our various policy machines set the London Bank Interoffer rate, the federal funds rate. So the short-term interest rates basically get set, and then the longer-term interest rates are determined by market forces, and that kind of trickles down to everyone else. After they, of course, get a spread on these basic rates, and the kind of prevailing trend this last decade or so has pretty much been cheap money, where interest rates are low, they encourage borrowing, and not as much on saving. And as a result, investments with a low level of risk, it's difficult to find really good yields on them in terms of return on investment. This is a definition of weighted average cost of capital, and a lot of these numbers are proprietary to the firm if it's a private company you're working for, and sometimes they don't want to give this info out. Occasionally I'll give them an array of a few discount rates and allow them to pick the one that's closest to what they like to see. But for weighted average cost of capital here, you're essentially looking at the return that's desired for the firm's equity and the firm's debt. And I've just done a quick breakdown here. So these values, like 8%, is pretty typical for a mature company in terms of cost of equity capital. There's also this concept of a beta for a firm, where it's kind of a stock picking term, but various companies and even industries are inherently riskier than others, and that can factor into this cost of capital decision as well. So once again, there's no consensus on discount rate selection. It is personal preference. It is what the client eventually would make a decision off of. But I do recommend going with HM Treasury, their Green Book, and currently I believe they recommend 3.5% real rate for 0 to 30-year projects. That falls for public projects, so most of those, they should be using that for that duration of project. As I mentioned before, the U.S. also has a similar mechanism. It's set by Code of Federal Regulation 436, and it's based on moving average of Treasury bond yields, and it's currently at 3%, which is actually the floor. It can't get any lower. If it was actually based on the moving average right now, it would be less than 1%, just because of zero interest rate policy where we are at the moment. Energy prices, they're more volatile than inflation. There's a number of reasons why this is, all listed here. But one I thought I would mention right now is monetary influences have been pretty unprecedented since 2008. Lots of devaluing of currency, quantitative easing, all of that can affect commodity prices. This is just a list of where to get some of this info. And I've got a little bit of analysis I did on this. Let me pull it up. Okay. So I took data here from Department of Energy and Climate Change. It's got figures in nominal and also in real using GDP deflators, so it's taking out inflation. So gas, electricity, oil, and I basically looked at what is the year-over-year change for different decades here. This is gas, and I came up with the last 10 years it's fluctuated quite a bit. In general, the 80s and 90s were a time of more price stability, and obviously the 70s had the energy crisis. So the 70s and the last decade have been more volatile, larger price increases. And since most of the LCC I do is in real rates, I will use these figures over here where it's over and above inflation. And I got the same thing here for water prices. Water prices are set by off-watt, and these are the year-over-year changes I came up with. 2000 was an interesting year, so I actually took out that outlier on this column, but mainly they seem to try and shoot for it is regulated, the prices for water, but it seems like 2% is kind of a common one, and that's in real rates as well. I thought I'd also mention at its source for pricing of these commodities, the U.S. and U.K. have a few different benchmarks that have actually been diverging recently for crude oil and natural gas for a number of reasons, one being supply side stuff like there's been a lot of what they call fracking, new ways of getting at natural gas here in the U.S. that's kind of added to the supply. So we use Henry Hub for pricing. That's in Louisiana. UK uses National Balancing Point. And then crude oil has got its ones mentioned there as well. This is just kind of summary of off-watt that is the regulator for water. I originally had quite a few slides going into detail on discounting cash flows in terms of the BLCC method that the U.S. uses for government projects. But I figured most folks are probably pretty familiar with that. But I just thought I'd mention that cash flow diagrams like this are a pretty good way of visualizing it, especially if the cash flows are different values and not annuities that are recurring each year. And I just thought I'd mention this special one. This is the formula for looking at an energy price escalation rate that's over and above your discount rate. And I believe all these slides will be available at the end, so I'm just going to go a little bit quick through these calcs. There are a number of output types that are of value here. Simple payback being the kind of go-to one for a quick analysis where there's no discounting. And sometimes what I found is that the discount rate and the escalating rate of energy prices actually kind of cancel each other out in some instances. And that can make a simple payback actually a pretty decent yardstick. But for capital budgeting decisions where it's a larger amount of money, I definitely recommend doing the more detail on it. So I've got formulas for these in the back of the presentation if you want to check them out. But there's a number of ways of looking at this: net present value, internal rate of return, discounted payback, and these other ones, net savings, savings to investment ratio. These are all, the ones at the end are ones you can basically compare cases between. Let me see. I think I'm going to pick up an example here for us. So this is a library in London. Did a energy audit for it. And this is just an example of a simple payback calculation, but we actually used cost of carbon in here as well. And I think we used it whenever carbon reduction commitment was still a bit hazy in terms of what rates they were going to use, but we tried anyway, plugging it in here. 12 pounds per ton, it looks like. And at the rates CRC was at the time, it was affecting it, but it wasn't really swaying it, changing the payback in a big way, not yet at least. I wanted to talk to you about risk and uncertainty, which are basically interchangeable in the world of finance. But the assumptions that we make are very important for what results come out of these analyses. And if it's something that I can spend the time on doing it, I will try and do a little sensitivity on higher budget projects. There's also a few other approaches here, like decision trees, probability distributions, and even up to Monte Carlo simulation, which I'll get into here.
Muted.
Risk attitude. We've got the concept of someone flipping a coin and offering you 1,000 pounds if you'd win. And then the question becomes, if I paid you guaranteed money, how much would it have to be for you to forego that coin toss? And that can reflect your risk attitude. If you say 500 pounds, then you're pretty much risk neutral. If you're willing to go for it for 300 pounds guaranteed, or to forego it, then you're risk averse, and the other way around is you're risk happy, I guess. You like risk. Let's see, I've got a sensitivity example here as well. This is for looking at a PV array in southern England, and this was right when they started talking feed-in tariffs and we knew what kind of rates they were advertising. So for this size array, we used the feed-in tariff rate, and we found that it definitely had an effect on the payback, more so than CRC would. And I realized that there have been some issues with whether the government's going to continue at what rates. But basically the point is, if there's any kind of subsidy available, I would recommend getting that into your analysis and quantifying it, saying what that benefit is. This one does have full discounting. Maintenance, as you can see, is constant. Since it's in real rates here, we're not having inflation in that number. And then electricity, that's going up by the escalation of of electricity costs. And you can do something, it's a bit tricky to do discounted payback period, but you have to pretty much sum everything up here, and then when you get to the year where you eclipse your capital cost, do a linear interpolation. I'm sure there is some software that can do it a bit more elegantly. This is some sensitivity analysis. This is what's called a spider chart. And a few different variables. I looked at energy cost escalation rate, did plus or minus 30% on that value and see what it did to net present value. And that ended up with this navy blue line, and did capital costs and maintenance costs as well. And basically you can tell by the slope of this line which one affects the overall result the most. And so I did the regression equations here. Highest slope was capital costs that had the largest effect. There's also kind of that same spider chart telling you the same type of thing, a tornado chart as well. And it's just a different way of viewing the same kind of data, the responsiveness of a variable. Basically, dependent variable change based on independent variable difference. Decision trees. This is kind of a capital budgeting decision way of viewing things. I'll open this up very quickly. I didn't do discounting on this one, but this is for that same library where we looked at, okay, we're replacing this air handler with a furnace, but what if we can either do the air handler with the furnace, a new one, or do a boiler system? And then from there, you know, is there a like-for-like swap, or is there some design fees needed in there? On the boiler system, I said, you know, what if you find asbestos? What does that do? So each one had a capital cost associated with each step, and I assigned probabilities to it. So you can kind of handle them all in isolation, and then you work the nodes back to determine the value of the overall path. And it ended up with the values I put in that this path had a higher expected value. So that can be pretty subjective where, I mean, hopefully these cost figures you could get pretty accurate, but some of these probabilities and whether or not there's asbestos, that can be a matter of judgment. So it's a neat tool for decision making, probably especially on larger infrastructure projects. But just be aware that it matters what you put into these things on your assumptions. So some of those nodes that are in that decision tree I didn't go into too much, but decision nodes, chance nodes, and end nodes. So at certain points you have a decision to make, and at certain ones you have a particular chance or probability it's going to be one thing. Decision trees assume you're risk neutral unless you use a utility function which can actually change your risk attitude on the outcome. Probability distributions. If you've got, let's say that PV example, a range of expected energy production, just the weather alone will fluctuate enough to have the energy production of PV change year to year. So we basically might say, okay, it's going to look close to a bell curve for that. Some other variables, it might be a sharper thing here. It might be higher on the left side. It might be really tall and not much of a normal distribution. And this is just another way of representing the probability of a variable being a certain value. So we are getting a bit into statistics here. Monte Carlo being kind of the complicated part of going into statistics. It's essentially usually a computer simulation that simulates a number of scenarios in quick succession, looking at distribution functions of different variables, and it comes out with all your different expected outcomes and where that falls on the curve. So if you have them all your variables as a bell curve, and then your Monte Carlo results will probably come out like a bell curve too. But that's not always the case for all variables. Here are a couple of software packages that do Monte Carlo. Once again, this is something more for larger projects with high dollar amounts that they actually are willing to justify this analysis. If you're just swapping a 100 kilowatt boiler out, it's just not worth spending the time on.
Hi Scott, you just got a couple of minutes.
Okay, well that was pretty much it. I've just listed some resources here, and there's some further calculations that we will have posted with the presentation later. So shall I turn it over and do questions at the end, or take them now?
Yeah, that'd be great. If we pick up questions at the end of the webinar.
Okay. Let's see. All right, I'll just turn it over to you now.
Okay, thanks, Scott. I'll take the control back, and we move straight on to our second speaker. As I've mentioned to people online, if you have any questions that you want to ask, please can you type them in. We won't be taking audio questions because it gets too difficult to handle. But if you type in questions, and then we pick them up and we will rebroadcast them ourselves here. So I'll just take control again at this end, and if I can find the right presenter. I'm in trouble just picking up the control here. Scott, are you able to pass it back?
Yeah, let me do that.
Great, thanks a lot. That's good.
Sure.
That could have been embarrassing. Right, okay, well we'll move on to our second speaker this evening. Our second speaker is Tony Willis from Sabian, and for those of us who are lucky enough to be in London, we'll also be benefiting from Sabian's hospitality later, as they're taking us out for a beer down one of our local pubs. So we'll enjoy that in London. I'm sure you can all have a virtual beer, wine, or orange juice at home, which you can enjoy. Okay, so hopefully you can see Tony's first slide here, and you can still hear us. And I will pass across now to Tony Willis, who will give a brief introduction for himself. Tony.
Thank you very much. Good evening, everyone, and thank you for the opportunity this evening. Just to give you a brief background to my particular experience, I come from a combustion and boiler control background, and I'd like to speak quite briefly and loosely in line with Scott's presentation about increasing boiler plant life cycle with retrofit controls. All right, okay. Sorry. Okay. Sorry, I missed the slide here.
No, you do the left arrow, take it back.
With increased pressure to reduce carbon emissions and higher efficiencies, organisations clearly are under a lot of pressure, both from a legislation point of view, operating costs, organisations' reputations with CRC, league tables, etc., and also internal and external stakeholders. Energy efficiency is one of the prime drivers that's implementing these demands. Clearly, hot water and heating generation can account for about 60% of your total energy costs. Increasing the efficiency of boiler plant can deliver significant savings and increase the life cycle of the plant. And we'll go on to that in a little more detail. Each time a boiler is obviously fired, it's quite a difficult thing to to equate, but it's quite well known that each time a boiler fires, the boiler comes under thermal stress, both from a thermal point of view and components and so forth. And replacing boiler plant can be very expensive. Applications is often different to the manufacturer's mean time to failure analysis. And as a part of that, with increased pressures to get higher efficiencies, some of the existing boiler plant that's actually in these buildings become underutilized, because obviously with more innovations and better efficiencies, this boiler plant doesn't shrink overnight. It's probably there from the original design and application it was designed for. So sometimes this boiler plant can be underutilized, or overcapacity as it often is referred to. And also with the advent of more efficient boilers, i.e. low water content, it's really important that boilers are not overstressed. Increased longevity equals increased control. Most of the biggest advances in recent times in boiler and combustion is actually controls. Building management, environment controls widely used in the commercial sector. BMS systems, as we call them here, and our friends over the other side of the pond, BAS systems, building automated systems. Whether you have weather compensation, outdoor reset, one aspect is actually to get better boiler load optimization. Boiler load optimization, so boiler plant only fires when required, delivering obviously less thermal shock. Mean time to failure, boiler components is increased. Clearly, if a boiler plant and its components, whether it's the burner components, if it isn't actually operating 6-7 times an hour, and it's only once an hour, it's putting less stress on all those components. Reducing energy consumption is part and parcel of that, and reducing maintenance costs and less downtime. Boiler load optimization is now widely used. Just as an example here in this slide, Retrofit optimizers installed on new or existing boiler plant. It's designed to prevent boilers from firing unnecessarily from the consequences of what's termed as boiler dry cycling, or equally it could be boiler short cycling due to overcapacity. Boilers firing can be typically reduced by 50%. That doesn't mean 50% saving, it means that the cycle of operations is reduced by 50% typically. Energy consumption can be typically between 10 and 25%. Clearly, having any retrofit control must fully integrate with the existing controls as mentioned with building management systems and BAS systems. There is nothing worse than having two systems conflicting with each other, so it's vital that these systems actually integrate and complement each other. And another aspect of this, that obviously any retrofit control mustn't impact on the design set points or the ambient temperatures or comfort levels of what this plant is actually serving. Just as a very brief overview on standing losses, all boilers to some degree will have standing losses. That's through radiant heat loss, sometimes through the flue systems depending on their configuration. But this is known as the standing loss. Boilers will cool down naturally over time whether they're delivering heat or not. known commonly within the industry is boiler dry cycling. Boiler dry cycling isn't a new phenomenon. It's been there since boilers were designed and manufactured. Many attempts in the past have actually failed. Simple time delays or increasing differential temperatures on thermostats do not work. Even buildings with sophisticated BMS controls very often miss this opportunity for savings. Clearly, optimizing a boiler is all about measuring specifically the load profile across that boiler individually, i.e. the delta T. A BMS system doesn't usually measure it in this way. It doesn't mean to say it couldn't, but typically it will be measuring a common flow or return temperature from the header. This is a blended temperature of all the boilers connected to it. It is physically impossible to identify which one of those boilers is dry cycling from a blended temperature. Hence why it's very important to measure across specifically that boiler. Just as an example, here we have a slide that's giving a 24-hour operation across a month. The ladder effect that you can see here is where a system has actually been put into essentially what's called a toggle mode. In other words, it's in a trial mode and it's actually doing what it's supposed to do on the tin on one day and not the next day. So these are alternate on-off situations. And you can see with the white segments there, this is where the actual retrofit dry cycle control has actually taken over and inhibited the boiler from firing under false load conditions, i.e. removing the times that it didn't actually need to fire, putting less stress on the boiler plant and burner components. During the off, the boiler is continuously firing, as you can see here, for genuine heat demands, and the boiler is dry cycling. And then during these segments where the actual optimizer is actually on, it is removing those unnecessary firing and still meeting the genuine heating demand. Just as an example here, these are two applications that were done in the US. Plaza Tower, this actually equated to a 22% fuel reduction and a 46% reduction in firings of that boiler plant. Another further case here, New Hanover County Schools, fuel consumption 23%, energy reduction, the reduction of boiler firings in this case was 59%. Now, I won't say they're all like this. This is just an example. It depends on the boiler plant, the application, and indeed the load put onto that boiler plant. But these are not, they're fairly commonly seen. Here is, if you like, some kind of UK examples. Clearly across any building estate, you have all different buildings of all different profiles and building fabrics. It's not a uniform saving that you will get across. All the variables, as you can see, are involved. But clearly reducing the times that the boiler don't need to fire will actually save fuel and put less stress on the boilers. Clearly the most efficient boiler is the one that's not firing. Just as a summary, primary objective is to reduce energy consumption and carbon emissions, but doing that will actually put less thermal stress on that boiler and boiler plant. Quite difficult to quantify, but clearly if a boiler plant is actually only operating for, say, 50% of its time, it's putting less stress on all those components and the induced thermal stress on the boiler itself. As I say, typical savings are achievable, typically between 10 and 25%. Reduced cycles of firing could be 50%. Obviously making sure the boiler fires only when really required. Reducing wear and tear on boiler plant. Mean time to failure can be extended low cost, minimal disruption. Vitally, it has to integrate with existing and complement existing controls. That is absolutely a prerequisite. And no impact on the original design set points or ambient temperatures of the plant. Thank you.
Thank you. Well, first of all, let's just thank our speakers for an excellent presentation. And now we've got some opportunity to take questions. If you've got any questions out on the webinar, feel free to ask those questions now. I will just get a holding slide up and then we can move forward with those. And perhaps start us off. Is there anybody in the audience here who would like to ask a question of either of our speakers? Yes, please.
I'd like to ask Tony, can you do a calculation to show if your original boiler was expected to do so many thousand hours of use before replacement? Can your figures reduce the calculator to say you would increase that life expectation by so many hours?
No, it's a very difficult thing to quantify.
Can you just say roughly what the question was?
Right, sorry. The question, can we actually put a direct correlation to reduce firings to increase boiler life? The answer to that is no, because of the different applications involved. For example, it might be a fully modulating boiler, it might be a high-low burner, it could be a single firing burner, and it is about the amount of thermal stress caused and as when. It is a very difficult thing to calculate per se, but to put it in simplistic terms, clearly a boiler plant is not firing repeatedly in the same way that you would expect a car that's driving down a motorway is going to probably have less wear and tear than a car that's being driven around town. That's why I say it's very difficult to quantify.
Any more questions from the audience over here? Ewan, you come up and you can ask it whilst so everybody can hear you at the same time.
I'm crowded up here. Ewan Rose, CIBSE ASHRAE Group. Very simple question. Would you say there shouldn't be any need for your technology because if people size the boilers correctly in the first place, you wouldn't need to optimize the running?
Yep, well the answer to that is yes, in a perfect world that would be the case, but unfortunately we don't live in a perfect world. Very often boiler plant is inherited, the goalpost moves, buildings evolve over time, and it could be that when the original design of that plant was done, yes, in the perfect world it was not ever going to dry cycle, it had fully modulating burners that had high turndowns, but as things have increased and things change, i.e. higher efficiencies, that boiler plant design is suddenly put under different criteria. So in a perfect world you wouldn't need such a product, but actually even the standard figures, 82% of boiler plant is over capacity generally. That actually exacerbates the problem too.
Okay, so that's a fairly startling statistic there. Scott, we can hear you, can we still?
Yes, hello.
I'm not sure if we can hear you here because our loudspeaker is very quiet, but so if you're able to speak, I know the guys online can hear you probably better than we can in this room. But I have a question. For you, Scott, from Spain, from Francisco, and Francisco asks, when we have many options and measures, what do you recommend to select the best one? Apparently he uses a GA. Is this the best option?
Sorry, is he talking about how to present the results or a software type in terms of the question?
That's all I've got for question, unless Francisco can type in a couple more words there, but are you able to address that one with the information you got?
Yeah, let's see. You mentioned also GA.
Yeah.
What is that now?
I'm
I think
not.
I missed the last part of the question.
Right, I'll repeat it. It says he uses GA. He uses a GA, and is this the best option? And he just says that's genetic algorithm. It's a genetic algorithm. We should have known, of course, but genetic algorithm, is that the best option?
Genetic algorithm. I'll be honest, and I'm not entirely familiar with that.
Okay, well, or alternatively, a neural net. He's qualified that with. Okay, I think we're perhaps at St. Francisco. Something you might want to take offline with Scott. I've already emailed Francisco with your email address, actually, Scott. He asked the previous question earlier, which I'm
sure that'd be fine.
So he can come offline with that one, perhaps. Okay, can I move on to another question? This one's from Jose Hernandez, and I'm not quite sure where Jose is, but Jose asks, how often are consultants and clients doing whole life cost analysis? Who drives normally the need for undertaking them? And how often and when will carbon be included? I.e., when's the price of CO2 going to be actually really involved in terms of a carbon tax? So I think perhaps if I can ask Scott first, just to give a brief response to that. So how often are consultants and clients using whole life cycle costs? And then I'll pass across to Tony for his experience in terms of the real frontline application of this. Scott.
Okay, sure. In terms of just the definition real quick, I tend to not usually include externalities and income and so on in the engineering calcs that I do for LCC. But assuming we kind of go with the definitions I put forward, I do get into it quite regularly. I do work for energy auditing for government buildings in the state of Texas, and for the most part, those are simple and quick flagging of energy conservation measures. We predict capital costs and energy savings, but everything is done on a simple payback basis and then ranked accordingly. But I also get involved on larger central plants, cogeneration systems, higher ed campuses, and these are the bigger projects where we definitely want to get into full discounting and looking at interest rates and so on. And maybe spend a bit more time on energy escalation and what we predict. And when it comes to the cost of carbon, it has already begun for Europe and the UK with the EU emissions trading scheme and carbon reduction commitment. And in terms of when it's coming to the US, that is a difficult question to predict because we're not quite there yet.
Okay,
one of the executive orders has...
Can I cut in there, and I'll go across to Tony, so I think he's got a couple of words
Okay.
as well.
Yeah, some, again, advances in this is actually looking at marginal abatement curves, looking where exactly where the best place this sits as far as energy conservation is concerned, life cycle replacement, so forth, can clearly determine to the client where he needs to spend his money to the best effect. Another aspect where I have direct experience in this is PFIs. Obviously, they may take over existing plant or new plant, and they, as part of that analysis, need to do life cost replacement analysis to actually specifically know, is their lease for 30 years going to be viable, and obviously put into their costs and how they've actually put their PFI together. So I think there are ways of actually analysing this from a practical point of view, and it's very important that, you know, every aspect, whether it's the carbon, the fuel, the boiler replacement, and maintenance and service costs are all incorporated.
Okay, thanks Tom, for that.
I thought I'd just chime in real quick. Tony, you started on this, and I think it's important. But if you're looking at the savings on a very small system and you're only expecting to save a couple $100, don't spend 10,000 pounds on design fees trying to figure it out. It should be appropriate to the savings that you're expecting.
Okay, thanks very much. Right, have we got any more questions in the room here for our panelists today? Yeah, we've got one. Would you like to come up and speak out here, and then our web audience can hear us without us having to repeat it? If you just stand in front of the PC, that'd be great.
Yeah, it's Michael Burney from ECD Architects. It was just to, I think Scott, you mentioned it just at the end there of your last comment. Could you maybe explain a little bit more about when life cycle costing would be appropriate, more in terms of the size of projects that you're looking at?
Sure. I would say we've actually, sometimes it comes around for regulatory requirements. Federal buildings, Department of Defense, we do get into some of that work, and they actually require us to do life cycle costing with full discounting on just system selection. And those can be all the way down to 20,000 square foot buildings for 10,000, so they're not very big. But kind of along those same sizes, just doing maybe a lighting retrofit to put some more efficient lights in a building of that size. It's been done enough times that a simple payback is usually a good enough indicator for them to go or not go with it. So it's really, when the technologies are new, renewable energy, a lot of people want to see more detail before pulling the trigger on those projects, and just larger size infrastructure, boilers and chillers and so on.
Okay, thank you very much. Just seeing if I've got any more questions coming in from the web. There's nothing at the moment, so if we've got any more from the room, otherwise we're heading towards our ending time anyway. But it's your last opportunity to ask a question if you're listening on the web. Otherwise we'll turn just to finishing up this evening. I can't see any in the room. I think everybody's just waiting to get down to see the Golden Lion now for the next part of the seminar. Yeah, there's no question coming over web. So I would just like to formally thank our two speakers tonight, and that's Scott West in Texas and Tony Willis here in London. You've both put, I know, a huge amount of effort into this, and I'm very impressed with both presentations. Unfortunately, I wasn't perhaps able to give it as much attention as I would have liked tonight, and I look forward to looking through those later. Scott will make a presentation available on PDF, which will be posted on the CIBSE ASHRAE group website, and may well be a link from the CIBSE FM website, but we'll certainly have on the CIBSE ASHRAE group website where you can download Scott's presentation, and we'll be able to put the Sabian one will also be up there as well from Tony Willis. I really commend both speakers for speaking tonight without using commercialism in their presentation. It really does add value to the meeting, and I'd really just like to thank them for giving so fully of their knowledge, and I do hope that those of you around on the web have enjoyed it as much as we have here. So thank you very much, speakers.